The matched pairs method of sampling is used to compare two treatments. This method reduces the variability within the sample since you are trying to match the subject's characteristics as closely as possible. It makes it easier to detect the differences within the two populations or treatments. Matched pairs is a block design. Remember, a block is a group of experimental units that are as similar in some way that affects the outcome of the experiment. In a block design, the random assignment of treatments to units is done separately within each block. Each block consists of 2 units matched as closely as possible into matched pairs. These units are assigned at random to the 2 treatments by tossing a coin or reading an odd or even digit number from a random number table. Alternatively, each block in a matched pairs may consist of one subject who gets both treatments one after the other. Each subject then serves as his or her own control. So let's look at this one. Investigators found 7 pairs of identical twins in which one twin lived in the city and one lived in the country, willing to participate in the study to determine how quickly their lungs cleared after they inhaled a spray containing radioactive Teflon particles. Now, when we look at the solution here, this is an observational study. We merely looked at people who were living this way. We didn't take and impose the treatment on these people, whether they're living in the city or living in the country. We did do something to them, but we observed what the response was like. So let's look at how we do this. So in the end, and like I said, I would do a matched pairs design because identical twins are similar on everything. At birth, I'd flip a coin and use the twin that was born first. If it's heads, then that twin will live in the country. If it's tails, they will live in the city. The second twin will live the other way. After a number of years, we will give them the Teflon particles and see how fast they can expel them. This method would be a matched pairs. And this would be the best because it now takes out every variable like genetics, lung capacity, etc. out of the experiment and makes so the only difference is where the child was raised. Obviously this isn't ethical, but it would be how we could perform a matched pairs. Let's look at a couple more. A local steel company wishes to test a new type of heat-resistant glove for workers who must handle the molten steel. The company randomly selects 100 workers to test the gloves over a 4-month period. Design an optimal experiment that will test whether the new gloves are more effective in resisting heat than the current gloves. Okay, so let's think about what this would be like if we did a completely randomized design. We would have 100 people. We would randomly assign half of them to use the new gloves on both hands, and the other half will use the old gloves. The problem is we might have some confounding in that experiment. The fact that people would have different jobs at the company would be a variable. Maybe some work with hotter steel than other ones. Maybe some work with steel more than the other ones. So we might end up with a group that does this more than the other group, and therefore we could have confounding by their job type. But think about it. Everybody has 2 hands. So what if we did this with each person? What if instead of giving them one glove, we gave each person both one of each gloves? And this way we can now make it a matched pair, so we can compare their work against themselves, the new glove against the old glove on the same job, the same person, they're working the same amount each time. So here's what we're going to do. Use each of the 100 workers as a matched pairs and give them one of each glove. We will use randomization to determine what glove the person will wear on what hand. With each of the 100 people, we'll flip a coin. If it's heads, that person will wear the new glove on their dominant hand, and if it's tails, they will wear the new glove on their non-dominant hand. The other hand will get the other glove. After a period of time, we will compare the wear of the gloves. Now, we could make this blind as well by having the 2 gloves look exactly the same. Therefore, the workers won't know which glove they are wearing. And now we have the matched pairs design using each person as their own pair. Go ahead and try this problem on your own, and we will just take a look at this one in class. Again, the same thing with this problem as well. Try this one on your own, and we'll look at the solution in class together. Alright, for this problem, I'm going to start off drawing it. So go ahead, try it at home, and then we'll take a look at this. But to start off, I'm going to draw this all out and see what we have here for this one. Okay, so how would you conduct this experiment as a completely randomized design? So we've got how many people? It's right hand, Paul Murky. Okay, so it doesn't quite say. So let's just say we've got 50 people. Okay, so we're going to start off with 50 people. Okay, then for a completely randomized design, we don't think about anything, and we just assign half the people to one treatment, half to the other group. So we want to put in here that it's random. And so we'll make 25 people here go to group 1. We'll make the other 25 go to group 2. Remember, completely randomized design. These 25 will go ahead and squeeze with their right hand. So they'll get treatment 1. test with the right hand. Okay, this group will be the treatment 2 group, and they'll do the test left-handed. And then what we'll do afterwards is we'll compare the strength. And there we go. There's a completely randomized design. Nice and easy. How are we going to make it random? Put all 50 names in the hat, pull out the first 50, or pull out the first 25, and without repeats to go to that first group, and we do it from there. And that's perfect. Okay, but is that the best way to do it? Are there potential flaws in this? Well, yeah. One group could have more strong people. One group could have people with bigger hands. Maybe that helps it out. But those are all things that could affect this. So how can we get around this? And so what we could do now is to do a matched pairs design. So instead of having this overall happen, let's have each person squeeze with both hands. All right, and so that's going to be the important part. So now we're going to be doing this as a matched pairs design. And randomization, so the next one, how would you correct them? So I would use a matched pairs design where each person squeezes with both hands. We will go to each person and flip a coin. If it's heads, they will squeeze with their right hand first, tails left hand first, then squeeze with the other hand. And there's our randomization right there. Because maybe someone would get better as they grab it the first time, they'd understand for the second time. So we want to randomize which way they're going first, so there's not that confounding variable of which hand you're squeezing with first. Then we will compare the differences in the left hand and right hand strength. Now we've taken out the variable about how strong someone is because they're squeezing with both hands and they are their own control group. And now we see again how matched pairs really is helping us out. Again, this is a type of blocking design. I'm just using each person as their own block, or sometimes I'm matching people up as closely as possible. All right, great. So that's matched pairs, in specific looking at the block design matched pairs.